Okay, guys, second stream of the day. Let's continue where we stopped. In this one, I'm gonna focus more on exploring certain parallel corpora for Serbian language. Let me, as usual, just share the link stream. The stream link. Oh my god, my brain. Latest stream will be focusing on Serbian corpora, finding some resources because our public bytext has 0 Serbian, Croatian, Bosnian, etc. Okay, Rafael wrote down something here. Let me see what he wrote, and let me turn on the live chat. I came across the curriculum learning issue. Wouldn't it be possible to realize it by tweaking a patch sampler? For example, it should only sample indices of valid length pairs at a given number of steps. I might have made a mistake. Are you sure that README link you mentioned is the right one? Whoops, it's not. Okay. Let me just edit this post quickly. What I try to do is go to Open NLLB. Oops, not OpenLB. GitHub NLLB. Exactly. Go here to the branch here. Find the modeling section. Here it is. And inside there was the curriculum learning post. So this one, and then just copy this, and then we just need to update this post so that we have the new link. Update the comment. This should now lead to the right location, and it does. Thanks for catching it. Updated, fixed. Nice. Okay, guys. Let's see the next step. I did basically dump this batch indices file while debugging in the last stream right here. So here it is, the pickle, temporary pickle. So let me copy that path. So what I want to do now is open the train.py file. See how do we construct let me see how do we construct the data set here. Just a second. So get train iterator. How can we just create the data set? So we need the task, and then okay, and then once we load the data set, self task data set will be here. Okay, so I want to just quickly hack something because this is going to be the easiest solution. I'm just going to say the following: analyze analyze data temporary. I'm just going to call this function, create it here. Super hacky because I just want to analyze something and understand something, so we don't really need to make it maintainable or anything. So here's the pickle location, pickle path. It's going to be this. We want to pass in the data set like this. We pass in the data set, and then call it like this. And I probably have to call, I guess, self analyze temporary. And so what we now do is load the pickle file. Just use my copilot to handle this for me. We don't have to print it. And then we now go through data sets and understand certain statistics. So the idea is this was sorted apparently such that similar length sentences are batched together. That's my understanding. So first of all, I'll have to here import quickly pickle. I'm just gonna locally import it here, and then let's just iterate through the data. For row in data, print the row. That's all we need really for now. And let's disable everything and just put a breakpoint here. Run train, and let's start debugging that code. Just want to quickly validate some hypotheses I have on how all of this works. Just move this here. Okay. We have a breakpoint right in here. After we load the data, there's some error. Takes one positional, but two were given. Of course. Whoops. Go here. We need also self, right? And we have to go through. This should now work. It's a self method. Self as the first argument, and then dataset as the only one we are passing in externally. So let's run this. So what will make sense? We'll want to index into the dataset and understand certain statistics of how this works. Notice if any outliers happen. It's gonna make more sense in a second. Okay, here we are. Load the data. Here is the data. And now we go through the rows and we print. And we go through the rows and we print. Awesome. So it works. That's the important part. So now, first I want to do is print the length. Let's print the length of the row. So that's how many data samples we have. So these many samples are being loaded or whatever. Doesn't have to be super precise. I'm just trying to understand what's going on. And then for index in row, we grab it from the data. So sample is going to be data set of index, exactly. So that sample, to the best of my understanding, has to contain ID, source, and target. So let's grab source. Nope. Wait. Just a second. Until we get to the collation, we just have to do it like this. It's just pure source like this. So Copilot made a mistake there, and then it's target like this as well. And so once we have the source, we want to understand what's its length. So we can maybe quickly batch some statistics here, aggregate some statistics like sample lengths empty, and let's just log maybe or like this source lengths and target lengths, and then just do something like this. Source lengths, we want to append. Can we do a length here? Let me think. I think this will be tensor, so I'm not sure whether length will work with. Let's just try this. And then what I'm trying to do here is now get the sum, print sum of lengths for source and target. Something like this and something like this. And next up, I want to find the maximum across lengths. Find the max across, find the element-wise max across source and target lengths. Let me see what it's gonna do. No, not that, element-wise. So we want to do either a max or just quickly create max lengths are gonna be like this. We go through both of them and find the max one. And then I want to see what's the sum here. Print the sum. No. How can you be so? This is an obvious one. Okay, so these should be, all of these should be hypothesis. These are all under 2084. That's one of the hypotheses. Especially the I think it's kind of the max length one. This one should be under 2048. I think that's how they've done it. Not completely sure. That's why I'm trying to analyze. And also, I'm expecting to see a diminishing number of sentences as we're progressing. So I'm expecting to see, if we grab, let me think for a second. By the way, this has to be done through sample like this. So we grab the sample, and then from sample we grab the source and target. Okay. So what should we do here? We need to understand what's the length of the row. Okay, we already have that here. And this should be monotonically decreasing. So row lengths, let's also keep track of that. Append that. And then go through the row and analyze the individual components and their max values. Right. This is roughly what I'm trying to do for now. Let's see. Let's stop this and let's rerun it. Stop and rerun. Again, make sure this is saved. Rerun. Let's see how this looks like. I have to say I'm so far pleasantly surprised with quality of code in FairSec. Other than the issue with FSTP, and it's very robust. Okay, so we have 488 samples. Let's go. Let's grab the data set. Whoops. Okay, something failed there, or we were just triggered to go and do this. Okay, let's see. What did happen there? So in row. Oh. Wait. Row is what? It's not a list. It's I guess empty array, numpy. Okay, we can't iterate like that through the numpy. So we have to do something like this, I assume. And then index and then grab sample, and that's a dictionary. And then we can do it like that. That makes sense. So otherwise it's gonna fail. Okay, it's gonna fail, I think. So yeah, retrigger again. And let's get to here. Okay, let's go. We're rowing data and then here. So we get the first index. and then we get the sample. And as I said, oh no, almost. Sample is a tuple. We have to grab the first one. So sample is gonna be data set of index and then of 1. So this is gonna be the right structure. I kind of messed it up there. So as you see here, this is the right ones. And then we pick up source and target. Okay. Attempt number 3. That's apparently a lucky number in Serbia. Let's see. Let me put a breakpoint here instead. And then maybe even here. Okay, let's stop here. Let's go. Let's go. Sample. Source. Can we do length on the tensor? Probably yes for these 1D ones, right? Or yes. Yes. Will not fail. Will not fail. Let's continue until we get to the very end here. So now we have a ton of these. All of them are 3, and then some of them start being 4. So that's for target, and for source, I think all of them are just going to be 3, 3, 3, all the way to the very end. Yes. Okay, so we find the max across them, and then print the sum, print the sum, print the sum. 1829. Now the question would be, why wasn't this filled up even more to 2084? Because that's our token limit. Why wasn't this put all the way there? I don't know. I should have done one more thing. One more thing. Distributed utils. Just to make this a bit more easy to debug. Otherwise, potentially issues might happen. Do we have config being passed? Let's go back to where we are. Do we pass the config? Do we pass the config anywhere here? Okay, alternatively, utils. We just need to see what's the rank of this file. Get the global rank. Get the global rank like this. And if the global rank is 0, then we do all of this. Let's go back to analyze script. So if distributed utils global rank equals 0, which is the master process, then we do the analysis, else just skip. Else just pass. Okay. Luckily we don't have to wait a lot, so I think I can just make a bunch of adjustments on the fly. So only for the 0th one, we're gonna enter here. Actually, I care about this one here. And we can just catch the other one on the pass statement. So if you're 0, you go here, otherwise you go there. So I'm gonna kind of, nice way to, yeah, that's it. Let's go. Okay, we can now ignore safely that one, and let's go here. Let's go all the way here. Whoops. Let's continue. Print, print, print. Let's do the same thing for the next one. Collect all of the data. So 408 samples are being loaded. Max is 2033, almost close to 2084. Let me think. Target sum. That's weird. That's a weird number. Because it's not divisible by 8, is it? And oh yeah, it doesn't have to be. what has to be divisible by 8 is the batch size. So 408. And the previous one, 488. That's the one that has to be divisible by 8. Okay. And then if we take a look at these are now mostly 5. And source lengths are mostly 3 still. Okay. So that means that's because we first sort the target and then we sort we sort the target and then the source. So because of that, source is always going to be strictly monotonic. Is that the word? My brain is just dead. Monotonic function. Monotonic function. Mathematics. Yes, it is. I'm mixing up Serbian for some reason with English. That's not a good sign. I have to rest, apparently. Okay. So, let's continue. And let me just think for a second. Let's go. 336 samples. Let's go. Okay, 1853. Let's go. Again, 288 samples now. Target sum is still 1826. Let's go. This is too small. Why would it be only 1405? And why only 168 samples? Something's weird here, guys. No sense whatsoever here. Why would this be only 900? Something is seriously messed up with that logic there. And now they go back to 512. So it seems it's cyclic. It's cyclic for some reason. So now we are again exactly at 2048. Let's go. 512 samples again. Okay. Again. Source sum. So it starts monotonically going down. 408. Let's go. Looking good. 408 still 360 samples. When I say sample, it basically means sentence. That many sentences. 336. Let's go. Reducing again, reducing. Number of samples. Let's go. 40 samples. 24 samples. So I guess the reason they don't get close to 2048 is because these are now longer sentences. So it's harder to squeeze in. If you squeeze in just additional one, you might mess up. But like again, if you have 24 sentences and you get 2000 something tokens, those sentences are not that long. We should be able to squeeze in more. 408 samples. Again, the number of samples increases. .408 again, 336, 288, and then reducing, and then 80, 24, 16, again, back to the old number, and then keeps on going, and then reduces to 16, and then goes back, and then reduces, and then goes back, and then reduces, and then goes back. And cyclically like that, we just keep on going. 184, reducing 868. But it seems that the upper boundary is always also reducing. So 168 now. It used to be 400 for this first number in the loop. Let me see, going down, 152. 152 now is the upper limit. Let's go. Now 32, 144. So that limit keeps on going down, but it's cyclic. 144. So we go down, 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 down. 136 is now the top limit. Okay. 64, 40, 16. 128 is now the upper limit. Okay. 128. I think that's the pattern. 120. So again, it's reducing. 112. Let's go. 104. 96. Definitely very, very weird pattern. 96 again, that's fine. As long as it's not a bigger number. 88. 88 again. 80. So that's definitely the trend. So it's like this. It goes like this, goes down, and then all of these peaks are getting smaller and smaller. But like my expectation was we don't have these peaks. My expectation was we have one peak and then we start going down, 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 down. So like the first ones are just like super, like very, very long batches where you have a lot of sentences which are all short. And then they slowly become wider and wider. But here it seems we're going like zigzag. $80. 72. 72. 72 again. 64. 64. 64 still as the upper peak. 64 still as the upper peak. Reducing 56. So we go below 56 now. 56 still. So reducing by 8. That's reasonable because it has to be divisible by 8. So 56, still 56. Still 56 at the peak. 56 sentences at the peak of the batch size. 48. So going down, 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 down. Okay. 48 still. Okay. So the trend is clear. The trend is clear. What is not clear is why do we have this pattern? It's completely gibberish. Maybe the function doesn't care as long as the number of padding tokens is minimized. That might be the case as well. Let me think for a second. Okay, these are still not padded. These are just raw sentences. As long as they're close in size, it's a valid batch. As long as you're close in size, it's a valid batch. Let me just close down the shaders a bit. Too much light. There is such a thing as too much light. Okay, so what's the thing here? I'm puzzled. I'm puzzled here. Let's just see, let's stop this. let's see what are the difference between the min and the max element of the length. So if we grab we do something like this. Across the source and across the target. What's gonna be the difference? And also find yeah, let's just do this. These should be fairly small. All of them should be very similar in size. Hello, Neros. Welcome to the stream, man. Welcome, welcome. Check out the Open NLLB channel if you haven't already. That's where we discuss everything related to the project here. Okay, let's grab the second process. Here it is. Let's put a breakpoint here and just start going through this. Actually here. Okay, so source max, source min. Okay, let's go. Let's just put the breakpoint here instead. Okay. Let's see what's the difference. Target max is 32 and min is 3. I guess that's a consequence of sorting these in such a way that you first have the min, you first sort according to source and then target. That's why for sometimes you'll have longer targets in some of those examples. Let's go. Let's just continue analyzing. Now the difference starts increasing. 47, 21. Okay, and now we go to 5. Let's go, let's go. This actually now makes sense. Wait. This now makes sense. This now makes sense. That's why we have zigzag, guys. That's why we have zigzag. Wait. This is why. This is why we have a zigzag. Because we go literally, we just follow those indices. We literally take, they're literally just chunking and So we have that sorted indices where sorting is across source lengths and then target lengths. And so that's why we see this target increasing where the source is the same. But then the confusion here still is, why didn't they pack closer to 2048? So you can see here a dramatic difference, 106 and 3 for some of these. $107 and 3. And then comes, so source is always, almost always very close. Okay, makes sense, makes sense, makes sense. What doesn't make sense is also this keeps increasing. So target is increasing, the difference will start increasing at one point between the max and the min. So as you can see here, 96, it used to be 62.38, okay, that makes sense. And then all of a sudden, you have 4. Aha, you have 4 because the source max changed. The source max is now 13, it used to be 12. So we got to that, got it. Okay, this makes sense, guys. What does not make sense is the length of these batches. Why are they not close to 22048, as close as possible? Let's get the sum again. Let's stop this. Let's quickly stop this. Let's get the sum. Compute sum for source and target. Sum, target, and print that as well. Let's repeat the whole run. Okay, let's go to the second process. Here we are. Hit run. So sum is, so this is the confusing bit, guys. We have 1829. We have a lot more space to put in more data. Could it be that because they are only 3 and 4, we can't get it divisible by 8 or something? The sum of lengths, 488 samples. So next up we'd have to add 8 more samples. If we add 8 more samples, we would have what? We would have 8 times 3 for source and 8 times 4 for target. We're still below 2048. Completely not clear why they're not putting in more tighter logic there. Okay, so let's quickly do the following. Get train iterator. Let's go back here. Let's go find the first batch inside of epoch batch iterator. Find this one. Okay, we found it. And now find how frozen batch is computed. Here it is. So batch sampler. Okay, so we have to batch sampler is what we care about. That's the one that gives us the frozen batches, the one, and that's the pickle we are currently analyzing. So what's the thing with that batch sampler? To get to it, we have to open get batch iterator from the class multi. What's the name of our task. The name of our task is translation multi-simple epoch task. Translation multi-simple epoch task. Let's find this. Here we are. Here is the batch sampler, and here is the function. So here's again what it does. We get the ordered indices, which basically means they're sorted according to first target and then source. And after that, we filter by size. So we just have the sentences between 0 and 512 in length. Well, it's never going to be 0 because of the filtering we do in our filtering pipeline in Stopes, but anyhow. So here's that magical function that I'm trying to understand exactly. And this is where I've dumped the data. This is where I've added the save pickle. Just after this, we basically pickled this object here, batch sampler. That's the list of lists. Okay. So this is 8, this is none, this is 2048, and these are the sorted indices. Okay. Let's stop the program. Go to train. Rerun it quickly once more. Just trying to see whether there is some bug in here. Probably no one from Fairsec would even notice. It's too complex of a code base. I'm probably the only madman who's doing these types of analysis. But just because I want to know how everything works. Okay. Just run. And we are here. Okay, run, enter. So this again gives us the maximum sizes. This should be cyclic in nature. I would expect this one to be cyclic in nature. Let's validate that hypothesis as well. So I'm saying that this here would be cyclic in nature because source increases incrementally, monotonically, whereas target is going to be increasing and then decreasing and increasing again. And so that oscillation of the target lengths is what leads to this type of behavior. So let's just import pickle. And let's say with open, and then I'm going to call it like this, basically, pickle. We want to have that right binary as f, and then pickle. We want to dump. We want to dump the data to that file with the protocol high priority or something. How do they call it? So pickle dump. Pickle dump. Like this. Exactly. Run this, and we saved it up here. So now let me quickly, while we are still debugging this, I'm going to copy a path here. Just go to a temporary file here. Just create a temporary file. I'm just creating a ton of junk all around the code base, but that's for the good of science. Let's go. Load pickle. Open it up. Okay. Import pickle. Exactly. Now go through these and let's just iterate. Let's just, or let's just visualize it quickly. Let's just quickly visualize it. Import matplotlib. Import matplotlib. Exactly. And let's just do plot number of tokens back. And just whatever, it doesn't even matter. Just show that and then print. Okay. Let's just quickly run this with no arguments whatsoever. No, that's not what I want. I want to go and analyze this. Don't go for me. Plot. Yes. Didn't fail. Yes, I think it's cyclic. Yes, 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 yes. Here it is. So it's cyclic in nature. It's cyclic in nature because we are sorting according to sources, and then targets can just explode. But these are obviously, something is not okay here, because we should have filtered out anything that has a ratio bigger than 9. So if we have this peak here, that's like 250. 250 divided by 9 is 27. 250 divided by 9 is 27. So is this one 27? Maybe. These are obviously bad translations. We can maybe, if we go to, let me share this screen capture with people from Discord, by the way. I'm gonna reply to him as soon as we wrap up this analysis. Otherwise, I'm gonna lose the context. Okay, so this is it. So I have a valid hypothesis. I had a valid hypothesis. Let's go. We can just wrap this one up. Go back to our script here. And we now have indices. So these are sorted, as I said, first sources and then target. And here we have, these tell us the biggest length. We already know what this is. Max tokens, we know what this is, 2048. And then max sentences. Okay, it might actually make sense, because what happens is they try to add the next one, but because it explodes, they can't get to 2048, because otherwise we'd overshoot. And so we keep this peak for the next round or something. Okay, it makes sense. It literally just chunks these. I think this literally just chunks these. But then why are we not running this in pure Python? It's not like this is something super complicated. Let me see. Let me see here. So we go here, batch by vector size, and this is something that's defined here in data utils fast. Data utils fast. apparently this is the one, and this is the function. This is the actual function. So here's the actual function. So well, let's actually analyze it, even though we can't step into it, right? Let's just see what it does. Let's see what exactly it does. Okay, let's open this up on the side. And let's go back to the code. So precisely the same signature, right? We pass in multiple needs to be 8. This is -1. This is 2048. These are the sizes and these are the indices. So these tell us basically how these are growing in maximum length across both source and target. Okay. Okay, let's go. Just one quick thing. What is PyX file, by the way? What is PyX Python? Python package for the creation of PostScript, PDF, and SVG files. Writing Python extension modules with C-like syntax. Why would you do that? Why would they do this? Okay, so if indices shape is 0, then we return, which is not. Assert that max tokens is either smaller or equal than 0, or that the max here is smaller or equal than max tokens. Wait. Max tokens. For us, max tokens is 2048. So this is false. And max across these is also going to be false because this is bigger than 2048. Or it's not, because we're just looking at the largest one is like around or almost 400. So why they're making sure this is the case is because if this is 2048 and a single sample is already bigger than it, then we cannot include even a single sentence. Okay, let's go. So in this is shape, we get the number of sentence pairs, and then we allocate a numpy array called batches and zeros of this length, and then view and view. Okay, these are just different views, and they cast to different format there. Okay, so we go through our indices. At every position, we keep stats about the last complete batch and tail. Every time when batch plus tail forms a valid batch, we append tail to batch. When this violates, we finalize running batch and tail becomes a new batch. There is a corner case where when tail also violates constraints. In that situation, gets added while this becomes a new tail. Okay. Okay, let's see. If tail max tokens, which is 0, is bigger than number tokens view, which is this, from the position, which is currently 0, that's going to be false. So we end up with the 0th size in tail max tokens. And then we increase this by 1, the end, and then if batch max tokens is bigger than tail max tokens, which it's not initially, so we add tail max tokens to new batch max tokens, and then new batch end minus batch start is the new batch sentences times the new batch max tokens. Okay. Overflow. Did we go over max sentences or did we go over this? If overflow, then we backtrack probably. Okay. Okay, so I think they're just doing simple logic, which as I assumed. Just a simple algorithm here. I would love to debug this. I'd love to debug this quickly. I'm just gonna rewrite this in a Python quickly and just insert it here temporarily and comment out this one just to make sure I understand exactly what's going on, guys. That's gonna be the easiest thing. Let's just grab this function. Why not? Quickly convert this to regular Python. So I'm gonna do the following. Below is a PyX implementation. Convert it to Python. Let's see whether Copilot can help me quickly clean this up, or if not, in that case, I'm just going to go line by line. It might need a bit more time to process the whole context as it's an autoregressive model. Okay, so I'm going to start by doing this. Exactly. Let's go. Let's go. Let's go. Let's go. Let's go. No, that's not correct. Max tokens, number of sentences, batch size multiple. Batch size multiple. Right, indices, number of tokens, and then we do this. Return. I write this. Okay. Let's see whether now it understands what I want to do. Shape. Yes. Yes, this looks good. It looks like it's copying now. Please tell me you're computing something. Overflow. Batches count, we expect 4 now here. Okay. Yes. Yes. Let's go. Let's go. Yes. That's the multiplication. Then goes the overflow. If overflow. Nice. 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 That's it. That should be it, guys. And that's how you use Copilot. That's how one uses Copilot to save a lot of time. Although we could have modified this as easily. I'm just lazy. So now that we have this, I'm gonna call this Python. I'm gonna go down below. I'm gonna comment out this and just say return Python version of this instead. And just pass in all of these arguments like this. Comment this out. Exactly. Put the breakpoint here and let's just analyze exactly what happens in the function. That's how we do it. Okay, go to train. Run the train with this config. Let's see now. Okay, Neros, do you hear me? Just to double check people hear me when I reply to them. I'm not sure whether you get the message on the other end. Okay, F5, run. Aha, Dan, thanks. Thank you. Okay, here we are. So again, indices are sorted according to, indices are put in such a way that if you take those indices and index into the data set, the source sentences are going to be sorted by the length, and then the target is going to be sorted afterwards. And that's why we have that cyclic pattern. This is just going to have the max size across the particular source target pair. Again, we saw that there is a cyclic pattern there. And max tokens tells us how much of tokens we can put in a single batch. 2048, I have a VRAM constraint. That's why I can't go above this, unfortunately, even though the paper proposes 1 million tokens per batch, although they train a much bigger model and all of that, but anyhow. And then batch size multiple is just 8. So that means we have to be divisible by 8. Okay, let's enter here. Put the breakpoint, hit F5. We are here. Let's quickly go through this and just go to the main body. So here's what happens. Initially, we grab this value, which is going to be, I think, this should be, from position, should be 3. Yes. So we iterate, we increase the position. And then we say, is this bigger than this? Which is false, which means we go here and grab tail max tokens, 3. New batch max tokens. So this is the current size of the batch, as far as I understand. And then we have difference between the tail. So it's like we are keeping two pointers. This is kind of Python implementation of what in C++ you would do with pointers. Tail and head pointers. And then you multiply this with the number of sentences, which is 1. New batch number of tokens. So this is the number of tokens. Okay. This now makes complete sense, guys. That's the part I was missing. It's counting in for the fact that we'll have to pad all of these sentences. So it's constantly keeping track of the longest sentence, which is going to be target because of the way how we do it, and that's why we have this batch sizes which are not basically not smaller than 2048, because I was looking at raw sentences. I was not looking at padded tensors. That's the thing. That's the thing, guys. Nice eureka moment. Awesome, awesome, awesome. I had an epiphany, no pun intended. So that's the thing. Because later when we grab those raw tensors, we call the collate function, which actually then adds the padding. So that's the thing. It's a bit more complex than, so it's literally just doing the simplest possible algorithm here, like just tracking head and tail pointers and then seeing how much it can advance the tail until it overflows, and at that point it just backtracks and starts the new search for the new batch. That's how it does this. Like, I already understand how this algorithm is going to work without even analyzing it, because I would implement that myself. Okay, so let's just go through it either way. So is there an overflow? Because we don't use the max sentences, we use the max tokens. The only question is the new batch bigger? If it is, we overflow. Otherwise, we continue. And then we also make sure that it's bigger than that the new batch sentences. The number is either smaller than this or divisible by, so that's the exception they have. It either has to be divisible or smaller than 8. And then if there is overflow, which there is no, we continue. Size matches with, okay, so here we got what? Okay, this was smaller, so that's why we were here. So now we do what? Batches ends view, batches count, which is what? Starts from 0. We add the new batch end, which is the pointer, and the number of tokens, and tail max tokens is 0. And we repeat this whole thing. So we ask again, is the number of tokens for this position, is tail bigger? No, it's not. So we retrieve back this. We progress. Is the batch max tokens bigger than tail? If it's bigger, then we would update. Otherwise, okay, so this is just silly way of writing this ternary statement. But this is keeping the max number of tokens. And then we see how many, this is again pointers, how many sentences we have. And then we multiply to get the new batch number of tokens. Again, this is basically just square computation of including the padding. They're assuming that the padding will later be a part of this whole thing. So let's see, when does this whole loop stops? It stops when we either hit the overflow or what? When is the batches count incremented? Either here or here. So we can just fast forward to that moment. Batches count. Okay, we hit the overflow because we have that many sentences. We picked up 196 sentences. And the number of tokens is above 2048. That's why we have to backtrack. So let's see what they do. Tail max tokens was 5. That's the biggest tail we've seen. If we multiply that with new batch end with batches ends view from batches count, we get the tail number of tokens, which is 40. New batch end minus this. So that's gonna be 8 times 5. I'm not sure what they've done here exactly. Let me just make sure it makes sense. So batches ends view was collecting until now the new batch end. Got it. So this keeps the pointer of the new batch end. So why is it only 488? Aha, because we were not hitting this. There was no overflow, and this was not divisible by 8. And that's why the last end was 488. This was the last legit one. And because of that, we have 40. We added 40 tokens here, and then max tokens. There is no tail overflow. And then 488 is the batch start. Aha, so this is the new batch start. And then we increase the count. And then we grab the tail max tokens to be the new batch max tokens. So we backtrack, as I said, we backtrack. And then if overflow, which is true, the new batch end is set here because we don't have to backtrack completely. We just stop there. Okay, that's it. That's exactly the logic that I was expecting. So we can now just iterate over all of this. Whoops, let's go back to the actual process we care about, which is this one. And let's just go here, and finally, we now have these splits. Batches, number of batches, which is 4,198, 4,200 roughly, and then we just pick all of those boundaries and we use that to split the indices. Exactly. So that's exactly the logic that I suppose was happening. I'm gonna stop this. We are done with this task. This was super nice analysis. I'm gonna just delete this. Let me just kind of backtrack, or I can just do git checkout, but I'm lazy. And this is it. This is it. Let's save this. This file is now unaffected. We can also delete the temporary file just to remove some of the junk here. And that's it. Let's just update with these new insights. Let me see whether we can update the README here. There was a note I left here. Line did make complete sense how the final indices were batched. Doesn't seem to be monotonic in size. If someone wants to do analysis around this and write a shorter report, that would be a valuable contribution. So we've done this right now. So I'm going to remove this and let me see whether I can just add something to the above text. So it sorts, filters out the samples that are too long. Okay. And then I think I mentioned something here. Filters, and then C, chunks the samples, or let's see, prepares batches the indices from A slash chunks the indices from A such that the total number of tokens in a batch, including the future including the padding, is below max tokens specified by our input arguments. That's it. Okay, that was the whole logic, guys. That was the whole logic. Everything makes complete sense. We have 3 types of padding. When you say 3 types, how do you mean 3 types? We have the left and the right. Truncate. We are not hitting that branch with the current setup for machine translation. So we just have left and right. And for both, the logic is the same, right? You always find the max sentence length, and you use that to figure out the shape. So you don't really care whether it's left or right. It's the same logic in that sense, right? Yeah, let me just think one more thing. When we were computing, the interesting part is that algorithm we just analyzed we'll have more than 2048 tokens, because it's not like it does sum between source and target. It just looks at the max element in the sequence, right? So effectively what it does, it makes sure that the bigger of the two is not bigger than max tokens. That's what it does. So it makes sure that neither target nor source tensors after padding are bigger than max tokens. Which makes sense, because ultimately when we say 2048, we want our source batch to be up to that number of tokens. We don't want the sum of the target and the source to be. The semantics make sense. I was just confused. Okay. The total number of tokens in a batch is below of source slash token slash target tokens in a batch is below max token specified by our input arguments. That's it. This is done in the batch by size script, or let me think. Okay, I'm just gonna leave it like that. Save that. Okay, Alex did push some changes. That's why I'm hitting these conflicts. What did it say about the pool? You have the virgin branches. Just a second, which branch am I on right now? I should be on the NLLB replication, okay? What's the best way? Wait, this is the easiest way, probably. Reset, just git log. Let me just reset. I would do something like this, but for some reason, it's not working on Ubuntu for me. This is not a hard reset, so I just have on-stage changes. Wait, what's going on? Okay. Now pull. Whoops. Exactly. And now we can just repeat the I'm lazy. Okay, and then just git commit. Exactly. That's it. We are done. Let me see whether my history makes sense. And it does. Cool. Okay, guys, let's go to the next section. This is done. Now, Serbian public bytext. Okay, there is a couple of sources I found out from people which are public. We're gonna analyze Opus. For start, and Makoku. And there are also these two papers. I think because I'll have a break before the next stream, I want to go through papers first. And then we can start, because this is going to take more time. This is more open-ended. So let's just start with papers first. Let me open up this one, and let me open up this one. Both of these papers are from Maja Popović, so I'm just curious to learn a bit more about what she's done. And we can just skim and see. So this is kind of specific to Serbian language, but we're going to be doing, highly likely other people will be contributing similar data sets for their languages. We also have mine data, but let's kind of skim through this. Okay, neural machine translation for translating into Croatian and Serbian is the title of this paper, and then we have on-machine translation of user reviews. Which one? What's the chronology? This one 2020, this one 2021. So let's start with this one. I'm gonna just quickly skim through this. In this work, we I think we have like 40 minutes until the end of the stream, so that's how I'm gonna roughly, that's the time limit we have. In this work, we systematically investigate different setups for training of NMT systems for translations into Croatian and Serbian. Two closely related South Slavic languages. We explore English and German as source, different sizes and types of training corpora, as well as bilingual and multilingual systems. We also explore translation of English IMDb, user movie reviews, a domain genre where only monolingual data are available. Translation of IMDb, interesting. First, our results confirm that multilingual systems with joint target languages perform better. Furthermore, translation performance from English is much better than from German, partially because German is morphologically more complex and partially because the corpus consists mostly of parallel human translations instead of original text and its human translation. So higher quality corpus for English as far as I understood. Partially because of corpus consists mostly of parallel human translations instead of original text and its human translation. Okay. The translation from German should be further investigated systematically. For translating user reviews, creating synthetic in-domain parallel data through back and forward translation and adding them to a small out-of-domain parallel corpus can yield performance comparable with the system trained on a full out-of-domain corpus. However, it is still not clear what is the optimal size of synthetic in-domain data, especially for a forward translated data where the target language is machine translated. More detailed research, including manual evaluation and analysis, is needed in this direction. Okay. Okay, we're gonna skip this for now just to see the whole paper first. Statistics of the parallel opus data. So English Croatian, English Serbian, German Croatian, and German Serbian. Just look at blue metrics. I'm gonna check it out. So we have here domain subtitles, news, and other. I'm not sure what exactly you mean, but I'm gonna see soon. Number of sentences for training. There's almost 30 million from subtitles and around million from these other domains. Similar statistics for Serbian. And then there is German to Croatian, around 10 million. And same for Serbian. Yeah, I know these are very low quality. I know these subtitles in general are very low quality, and apparently Opus mostly contains those. Let's go. Statistics of the movie reviews did. By the way, let me just paste the paper here in case you want to open it up, and also here. Paper reading right now. Serbian author trying to get some Serbian, Croatian, etc. by text. Okay, so here statistics of the movie reviews data, corpus, different corpora here, languages. This is mostly Croatian only. Number of sentences, this is less than a million combined, or around a million. And then similarly, this is Serbian. Okay, also similar number of sentences here, maybe a bit more. Okay. Results from translation from English into Croatian above and Serbian below. Corpus size, percentage of the target language, training time, and the 3 automatic MT scores. Blue, CHRF, and character. Okay. English to Croatian. Size. And here are the metrics. This is embarrassingly low for these ones. And then 32, that's, I guess this is around what you would expect. I'm not sure how to parse this though. How do we parse this number? Like, it's 33.7 when you trade 5 days. What's the percentage of creation here? What is this? This is the percentage of the target language. Size. So when trained on what? On English to Croatian plus Serbian full clean, whatever this means. And what does it even mean to have only 32.9%? That means that what, 11% is Serbian as the target, because otherwise it would not be a parallel corpus. I guess I'm interpreting it correctly. And then for Serbian, similar here. Okay, we're gonna check the details a bit later as well. And then for German results, okay, this is just terrible. Definitely not the best results in the world. That's what they said in the beginning as well. Summary and outlook, and then acknowledgements and references. Let's see what they say in the outro. And then we're gonna read the rest of the paper. For translation, good blue. Well, it depends on the language, right? I'm not sure if 50 is a bit too much. Even for deep L, I think for some of these, like English to German, it's around 40-ish. So it depends on the language, right? Some languages are going to have much higher blue, because blue is ultimately a very bad metric. It's just like superficial lexical analysis of n-grams. And then there are all these neural metrics which also come with their own caveats, like Blue Earth or Comet or whatnot. Okay, this work presents a systematic. Thanks a lot for the engagement, by the way, Dan. So this work presents a systematic investigation of different setups for training NMT systems for translation to Serbian and Croatian, two closely related South Slavic languages, which is the understatement of the century. We explore English and German as source languages, different sizes and types of training corpora, blah, blah, blah. We also explore translation of English IMDb. Only monolingual data is available there. Joint target languages performs better. Much better than German. They're just repeating everything from the intro. Okay, still for both source languages, our best systems perform better than the two online systems, Google Translate and Amazon Translate, whereby the Amazon systems for translating English into Croatian are comparable. By the way, I just had a call this morning with a guy who started the Amazon Translate project. Just a fun fact. And he's actually, yeah, I don't want to say anything else, otherwise I might reveal his identity without him allowing that necessarily. So yeah, for translating, just look at the Serbian part of the Opus dataset and everything will be clear to you. Fuck, man. Can you paste a couple of sentences? For translating user reviews, creating synthetic in-domain parallel data through back and forward translation, I think we might be able to get some data from Jertek. That's a Serbian group that's been building these datasets, and those might be much higher quality, although they come with non-commercial license. So we'll have to see, make a deal with them or something, how we can collaborate together. For translating user reviews, creating synthetic in-domain parallel data through back and forward translation, and adding them to a small out-of-domain parallel corpus can yield performance comparable with a system trained on a full out-of-domain. Still leave some important questions open. Okay. Let's go. Hold him for now, neka ostane u pritvoru. Well, that's... I guess because it's very contextual. That might be a good translation, but it's not a literal translation given that sentence is a context, right? Yeah. And what's this? Results for translation of English IMDb movie reviews into Croatian and Serbian. Okay. Trained on this. Did they mention the hardware they've used? Okay, let's read this. There is not that many lines. Oh my god, my computer mouse is screeching. Let's go. Whereas South Slavic languages are generally less supported and investigated in NLLB, they have been explored in the field of MT. Nevertheless, a large part of the work deals with the previous state-of-the-art approach, namely phrase-based statistical machine translation. Okay, these are familiar names from my LinkedIn post. While much less work can be found about the new state-of-the-art neural machine translation. In this work, we focus on NMT into Croatian and Serbian, two very closely related South Slavic. We explore two source languages. The main goals of our research are to explore two source languages, each of them with different sizes and types of training corpora, as well as to test our systems on translating the English user reviews, a challenging domain genre where no parallel training data are available. For these purposes, we train bilingual and multilingual systems. For translating English user reviews, we also explore different types of synthetic parallel in-domain data, which is a widely used practice in NMT. So I guess, so the ultimate goal is to what? Translate user reviews, and that's why they have later this paper, on machine translation of user reviews. I guess that was for some reason important for these guys. Adept Central, what organization do they belong to? No idea. But yeah. We also explore different types of synthetic parallel in-domain data, which is a widely used practice. We explore two types of synthetic data, back-translated and forward-translated. BT data consists of in-domain target language data and their machine translation into English, whereas FT data contains of English data and their machine translation into Serbian and Croatian. All our experiments were carried out on publicly available data sets. For all our systems, we present three distinct automatic MT evaluation scores. Training corpus size, percentage, training time. We also present for two systems, Google Translate and Amazon. Fair enough. Do they mention GPUs anywhere before we continue? GPU, hardware. I'm gonna ping Maya and just ask her what was the compute they've used. Because we're connected on LinkedIn now. Let me just ping her quickly. I'm obviously not gonna show you the messages, but let me just send the message there. That's a perk of knowing the authors. Hi, I see yet another sentence that they unpasted. Well, at least you're here, and that's all that counts. No važno je da si ovdje. Yeah, well, that's why I'm very pessimistic about making a distinction between Serbian and Croatian and Bosnian. There's gonna be a ton of, like, I don't know, like even if you went to like South Serbia, to like Niš, Vranje and those places, if you read that Serbian, I think you would probably confuse it. You would think it's from a different country more than like the difference between Croatian and Serbian. So like, I don't know. There are all of these subtle variances. I think ultimately if you just have Latin script versus Cyrillic, that can be kind of decent. Like you can separate those two, but like other than that, it's gonna be a hard task. We can probably chunk everything together. Croatian, Serbian, Bosnian. We'll see what makes the most sense. As already mentioned, a large number of publications deal with the statistical approach. An overview of Slavic languages is given there. Translating from Croatian into English for tourism domain is presented there, while factor models for the same language pair were explored there. Similarities and differences between Serbian and Croatian in terms of building are investigated in this work. Okay. Linguistic phenomena posing problems. Publicly available. With the emergence of NMT, several publications have compared its performance with these statistical approaches. Well, I mean, this is also statistical, but just neural. Translation errors from English into Croatian are analyzed in this work. Discourse phenomena explores linguistically motivated issues for the English-Serbian language pair. Different training setups for NMT from English to Serbian Croatian were first investigated there. They explored individual bilingual systems for each language, systems built on merged unlabeled data, as well as multilingual systems built on merged labeled data, namely with a language identifier in each source sentence. They investigated combinations of unlabeled. The results showed that the multilingual approach with a language identifier is the most promising. NLLB does the same thing. We prefix both the source and the target sentences with language tokens. However, they carried out the experiments only on a very small TAD corpus consisting of about 100K segments for each target language. In our work, we systematically investigate different corpora with sizes in the range of 300K to 40M segments. And then, okay, however, they explored only Serbian as target language, trained on a very small corpus. Okay, I forgot, like, I don't remember the last time I saw out of domain and in domain. Everything is in domain when you're dealing with large language models. For all of our systems, we use the publicly available Opus Perl data. The vast majority of these resources for the desired language combinations consist of open subtitles. For English and both target languages, we also used Set Times News, Bible, Tilde, EU Bookshop, QED, and Tato Eba corpora. I've seen this name being mentioned across the spectrum, across various works. So for English and both targets, we also used these other data sets. In addition, we use global voices for Serbian and Croatian, English, WAC, TED, and Wikimedia for Croatian. For German, we only used open subtitles because other corpora are rather sparse. So that's probably the reason why German is so bad. However, including these corpora might be interesting for future work. Let me just quickly check something. There was this, somebody linked this overview of various work in the Serbian NLP literature. Let me just see and find the paper. I think it's this one. So somebody just done a survey across different corpora for both monolingual as well as monolingual Serbian corpora and then parallel Serbian corpora. And I think that was the main thing. This is corpora for sentiment analysis. Let's go back up here. Let's zoom in here and let's see whether some of these names are mentioned here. Let me quickly check. I have to put it on the side. So set times, news, Bible, tilde. Let's see whether any of those are mentioned here. This is from 2023. This is a newest paper, newer than the one we're reading. Parallel Serbian corpora. Set times is mentioned. Serbian English WAC, which they mentioned only for Croatian. Bible. Open subtitles, which is, I guess, from Opus. Yes, this guy. I actually also wrote him an email. He did reply, but he's currently super busy to help around the project. I actually wanted to get him involved. The guy behind Opus. He's from Finland, just FYI. What else do we have? Do we have tilde, QED, and Tatueba? I doubt it. I don't see it here. Okay, so there might be some additional things we could take a look in. Okay, just a second, guys. Okay, where did we stop? We were analyzing the particular data sets for Serbian Croatian. However, including these corpora might be interesting for future work. Okay, so only open subtitle for German. The original parallel data were filtered in order to eliminate noisy parts. Too long segments, more than 100 words. Segment pairs with disproportional sentence lengths. Segments with more than 1/3 of non-alphanumeric characters, as well as duplicate segment pairs were removed. Okay, I think we're doing most of that type of filtering ourselves. So we removed too long, whereas too long is defined in our code as 1050 characters. Too short, I think it's like 5. And then ratio of 9. Disproportional sentence lengths. Duplicate segment pairs. We do duplication as well. Table 1 shows the number of remaining segments which were used for training and testing. For testing English systems, we used 800 segments from subtitles and 200 segments from news. We only use subtitles for German. Okay. So around 24 million here, 30 million for Serbian. Okay, just to get an understanding of the order of magnitude of the sentences for training. Translation from English is also tested on publicly available texts. Translation from English. EMDB corpus, consisting of English user movie reviews from IMDb and their human translations into Serbian and Croatian. This test set, also used in this work, was compiled from the publicly available IMDb corpus created for sentiment analysis. Link 6. For this test set, we explored the use of synthetic data obtained from the following monolingual in-domain data. Movies, Croatian and Serbian texts collected from websites dedicated to movie overviews and cinema programs. This corpus is very small, consisting of about 100k Serbian segments and 5k Croatian segments. Okay. Selected, extracted from the mixed Croatian and Serbian web data, HRWAC and Serbian version, using the feature decay algorithm, FDA. FDA selects sentences from an initial set S based on the number of n-grams which overlap with an in-domain text seed and adds these sentences to a selected set cell. In addition, in order to promote the diversity, the n-grams are penalized proportionally to the number of instances present in a cell selected. During the execution of FDA, candidate sentences from the set S are selected one by one according to the score defined in 1. So they have just some score, n-grams like overlap with the seed, and then normalized by the length. The sentence with the highest score is removed from S and added to selected set. The count of occurrences of n-gram NGR in the selected set is updated so that in the following iterations, this n-gram contributes less to the scoring of one sentence. Okay, for our experiments representing the set S and the movies data were used as seed. So that's the in-domain data. Before applying FDA, the undesirable sentences were removed. Okay, in this way we obtained about 50k selected segments for each target language. Got it. And then IMDb, English data consisting of about 600k IMDb movie reviews, which were not used as a test set. English Amazon movie reviews from the Amazon product review collection. We used the first 1 million segments from about 50 million total for the experiments described in this work. Using more of these data could be an interesting direction for future work. Okay. And then finally they mentioned the synthetic data. The Serbian and Croatian data, movies and selected, were translated into English by an NMT system in order to create back-translated synthetic parallel corpora. The English IMDb and Amazon data were translated into Serbian and Croatian by an NMT system, thus providing FT synthetic parallel corpora. In order to obtain a balanced corpus in terms of the two target languages, we translated half of the IMDb and half of the Amazon into Croatian and the two other halves into Serbian. More details about the NMT systems used can be found in the next section. Detailed statistics can be seen in table 2. Okay, so they augment movies and selected with back translation, and IMDb and Amazon with forward translation. So they have those 4 different sets: movie reviews and opus. Okay. So other than that, why do they have exactly this movie reviews? Let me see. Translation from English is also tested on publicly available texts. Okay. So do they additionally fine-tune on this data and they mainly train on this? Or is it a combination, or like, that's unclear yet. So they have like two separate parts. They have the opus and some additional ones for Serbian especially, and some for Croatian. And then they have the movie reviews, these 4, which are augmented using synthetic data approaches. They're very small in size though. Like a bit more than 1 million. Okay, let's see what they say here. Let me just read what Dan wrote here. Created by a Serb tokenizer. I'm not sure what you meant by the first sentence. Fine-tune the LLM model. It has already seen the Serbian language in its initial training. The fine-tune of the model itself would be done with Alpaca. Maybe this will help, I don't know. For machine translation, that makes sense for LLMs, but we here are first training empty systems, right? So for machine translation systems, you want the model to be stupid and just translate the you don't want conversational agent, you don't want instruction tuning to do here, right? So it's a bit different setup, but like I did consider Alpaca if for by the way, Alpaca is not a technique. Alpaca is just like the data set that the Alpaca Stanford team used. It's just a instruction tuning set of prompts and completions from, I think Alpaca was GPT-4 if I'm not wrong. So yeah, it's a bit different context, but still thanks for the suggestions. All our systems are based on the transformer architecture and built using the Saki implementation. Interesting. Wow, what's that? Sakai, or however you pronounce it, Saki. AWS stuff. Open source sequence to sequence framework. Interesting. I've never heard of this one. It's not really popular as well. There is a decent amount of activity. It's not dead. The systems operate on subword units generated by BPE. We set the number of BPE merge operations at 32,000 both for the source and for the target. We do not use shard vocabs between the source and the target languages because they are distinct. Okay. For multilingual systems, on the other hand, we built a joint vocab for the 2 target languages because they are very similar. Wait, I didn't catch this. So we do not use shared between the source and the target. That makes sense. But then they say for multilingual systems, on the other hand, we built a joint for the 2 target languages because they are very similar. Well, you've done the same thing for the target of the previous sentence here. So what's different here? These systems are built using the same technique as these guys, namely adding a target language label to each source sentence. All the systems have transformer architecture with 6 layers for both encoder and decoder, model size of 512. Okay, these are super small models. I already trained a bigger one. So because it's like 6 layers, I assume this is 512. This is less than 200 million probably. Much less. For training, we use Atom Optimizer. They have early stopping. Okay. So for low resource settings, they just have a different parameters. Okay, and then they say what? The following setups were investigated for translating from English into Croatian and Serbian. Clean data only. Okay, so these are, we have to read this to understand the tables later. The bilingual English to clean Croatian and Serbian, and multilingual low resource systems are trained only on news and other data from table 1. The segments in these texts are mainly properly aligned, so we refer to it as clean. It is worth noting that this corpus is rather unbalanced in the terms of target languages, as can be observed from table 1. There are only about 300k segments for Serbian and about 1 million for Croatian. What? Where can it be seen? News and other data from table 1. 1 million from Croatian. 300,000 for Serbian. Okay, so that's the clean part. Subtitles only, first 2 million. In order to compare bilingual and multilingual systems in a balanced scenario, a small subset of subtitles is used. The bilingual system, English to Croatian sub 2M, are trained on the first 2 million for each target language. For the multilingual system, the duplicates were removed after joining the corpora, so that 3.6 million segments remained. Okay. Cleaning. Subtitles contain a number of misaligned segments even after the basic filtering. Therefore, a multi-source system in the opposite direction was trained on the same data and was used for removing segment pairs with the negative log probability larger than 2 from its own training corpus. Let's just read this again. Subtitles contain a number of misaligned segments, okay? Therefore, a multi-source system in the opposite direction was trained on the same data and was used for removing segment pairs with the negative log probability larger than 2 from its own training corpus. Okay, this is just some filtering using the language models. The opposite translation direction was used for cleaning because of different complexity levels of the languages. Probabilities provided by an empty system are usually more reliable when translating from more complex languages into less complex ones. After cleaning, the number of parallel segments is reduced to 2.7 million, and this clean corpus is used to train a cleaned multilingual system. Okay. So they just have a ton of these different splits. And this comes from subtitles as well. So they start here with 2 million and then they join to get 3.6 and then they filter additionally and they get 2.7. So this is opus mostly, and this is the non-opus. Subtitles, cleaned first 2 million plus clean data, oh my god. The multilingual system is trained on the cleaned 2.7 million segments from subtitles merged with the low resource clean data, consisting in total of 4.1 million. This system is used as a baseline for translating English movie reviews. A multi-source system in the opposite direction is trained on the same data and is used for cleaning the full subtitles corpus as well as for back translation of movie reviews. And then full data. the multilingual system is then built on all clean and all clean subtitles. Okay, and then similarly for German, let's skim this. Okay. Let's continue. The main challenge when translating this test set is that there are no readily available parallel corpora of movie reviews which could be used for in-domain training. Okay, so they take the baseline and they enrich it somehow on the clean data together with the clean first. On the clean data together with the clean first 2 million segments from open subtitles. On the baseline system data enriched with back translated movies. Movies and selected. Forward translated IMDb and Amazon. Results. Translations from English and German. Summary and outlook. We wrap this up. So we're almost done. We evaluate our systems using the following 3 automatic scores. Okay, we already know what these are. In addition to automatic scores for each of these systems, we report the size of the training corpus, training time in terms of days, without mentioning hardware, which is completely, is not really informative if you don't know what hardware because I mean, yeah. In a couple of days on a super cluster, you can train whatever you want. Translation from English. We should force people to just mention compute hours on which device. The results for translation from English are presented in table 3. We've seen all of this already. Let's just see. As expected, multilingual systems are better than bilingual for all setups, even for the unbalanced clean. Improvements are smaller for creation. Data quality matters. Adding the first 2 million clean segments from subtitles to the small clean data results in scores which are approaching those obtained by full data. Okay, although the corpus is much smaller. The training time is more than two times shorter. Okay, adding German data does not prolong the training time. So we also don't know how many steps they've made across the data set. Okay. So the best results are multilingual, clean, big. So we want to have big, clean data and more languages, more data. Okay. And finally on the full. Cool. That's it. I guess I mostly cared about the data. So they use Opus, so the subtitles mostly, and then they use a couple of other ones here mentioned in the beginning. Set times, news, Bible, blah blah blah. And then they also have these 4 which are augmented, which we don't care about because for some reason they were just focused on the domain of movie reviews, whereas we don't really want to specialize in any of the domains. IMDb, Amazon, movies and selected. I'm gonna ping Maya and ask her for links from the paper as well, like data sets. Where did they get the other data sets? Okay, and then there is this, a machine translation of user reviews. We'll check this one out after the break. There's only a couple of pages here to read, like 7 pages. We're gonna wrap this one up after the break. Let me see whether we have anything else. So this is the one we wrapped up already. Okay, and then we're gonna go through Opus and Makoku and just analyze some of these data sets and see what we can integrate into our download data script, so we can increase the support for Serbian and Croatian and Bosnian and Montenegrin. I'm not sure how you pronounce it. Okay, guys, that's it for this stream. Solid work. We understood exactly how this logic of creating the batches work. We analyzed that, and then we read the paper, and I think that was the main focus for this particular stream. It was a short one as well, maybe 2 hours or something. So yeah, cool. See you in roughly 2 hours. I'm gonna continue the stream 8:30 p.m. CET, Central European Time, and until then, cheers guys, see you.